Hey everyone, welcome back, and today let's solve Leetcode problem 1415, titled the kth lexicographical string of all happy strings of length n. So a happy string is a string that consists only of the letters of the set A, B, C, and S at index I is not equal to S at index I plus 1 for all values of I from 1 to the length of the string S minus 1. The reason why it goes from 1 to the length of the string S minus 1 and not from 0 to that value is because this string is considered to be 1 indexed. And what that really means, basically no two adjacent characters or elements in the string should be equal. Now, they give us some examples of how that would work as well. All the strings A, B, C, A, C, and B, and even this large string here, they would all be considered happy strings because if you actually iterate through the string here, you'd see that no two adjacent characters are equal. Whereas in the strings AA, BAA, or ABA, BBC, all of those strings have at least one pair of adjacent elements that are equal with each other. So they would not be considered happy strings. So now we're given two integer inputs, n and k, and we simply need to consider a list of all happy strings of length n sorted in lexicographical order, meaning it's sorted in ascending order based on their lexicographical values. And we want to return the kth string of this list, or return an empty string, if there are less than k happy strings of length n. And when they really say consider a list, basically they want us to generate that list of all those strings of length n, and they want us to return the kth string of that corresponding list that's again sorted in ascending order based on lexicographical value. So in example 1, we have our input n and k to be 1 and 3 respectively, and what that really means, basically, we want all the strings of length n, right? So basically of length n, and we want to return the kth string of that list. In this case, k is 3, and the list would be ABC. Notice how all ABC, all of these strings, are indeed length 1, because of course they are only one element, 1, right? And the third string of this list would be C, right? Why do we want the third string? Well, because K is 3, and we know that this is actually index 3 and not index 2, like we're usually used to seeing, because this string is 1 index. These are all the happy strings of this length n, or of this length 1, and that third string in this list that we would generate would be the string C, right? The reason why we want the third string, again, because that is the value of the K value or input, and so we output a string C. In example 2, we have our n to be 1, and in this case, k to be equal to 4. Now, going back to the last problem here, we saw that there only were 3 strings that were considered to be happy of length n. We didn't even have 4 strings, and so there is no 4th string to even output, and since we only have 3 happy valid strings of length n, or of length 1, we simply have an output of an empty string because there is no 4th string or kth string to actually output as a valid output in the context of this example. And finally, for example 3, we have n to be 3, meaning we want all of the valid or happy strings of length 3, and we want to return the 9th or kth string in that list. In this case, the 12 different happy strings that we can generate that are valid and or happy as such of length n or of length 3 would be these corresponding strings, and the 9th string in that list would simply be CAB, and so CAB is the output that we have for the problem. So we say that n is going to be within 10 and k is actually going to be within 100, and that leads us to the main observation to really solve this problem that we can really make. Notice how we want to generate all the valid strings as such in this range, and we also have relatively very small inputs. Now, usually when we have a problem structure like this almost always is going to be a backtracking problem, and this problem is no different. This is a classic, very straightforward backtracking or recursive DFS problem, and it is a very good problem to really talk about, right? We are actually generating the lexicographically ordered string, and so to actually build or explore all those valid strings in order, backtracking is the way to go. And the way we would kind of formally say that would be we'd use DFS, or the depth first search algorithm, with backtracking as well to actually build or generate all those valid happy strings in that range. And the lexicographical order that constraint basically signifies that we always have to try adding an A first, then we try adding a B, then we consider adding a C. Why do we do it in that order? Well, because A is lexicographically smaller than B, and B is lexicographically smaller than C. And we want to keep it in ascending order where the smaller lexicographical values come first. And so we want to first try A, then B, then C in that lexicographically ascending order. And also finally, to always ensure that no adjacent characters are the same, to kind of fulfill that valid string approach as well, before we actually append any character that is, we first have to check, is it the actual same character as the last character in the current string that we're currently working on? If it is, we can't add it because we don't want to have an invalid or non-happy string where two adjacent characters are equal. So basically, for a high-level rundown of how the solution is going to work, basically we use that backtracking approach to actually generate all the valid happy strings of length n using that kind of recursive or brute force approach. And we're also going to keep track of the count of the number of valid strings that we find, and then finally we simply have to stop when we actually reach that kth valid string. We don't care about all these strings after that kth valid string. We stop the moment we reach the kth valid string that we build. And if we generate fewer than k valid strings, well then, like the problem says, we simply return an empty string that signifies that we don't have a valid input. Right, so basically we're going to be having a count, which basically stores the number of valid strings. We're going to have a result that's basically going to store the kth happy string result once we actually find it or build it. And we're going to have a backtracking recursive function to actually build all the happy strings. And it's going to take in one parameter current string, which I will explain in a few seconds, or in a few minutes rather. So with that high-level solution out of the way, let's go ahead and get into the code here and see how we can actually implement that code. So first of all, like I was talking about before, I'm actually going to initialize a characters array, and this is going to be, of course, 3 characters. That's going to be the 3 characters that we're allowed to have, A, B, and C. And you guessed it, that's exactly the 3 elements that we're going to have in this list, A, B, and C. And in this case, we want to have them in the form of characters or string data types rather than just elements or numbers, right? Basically, this array characters or chars, it's going to actually contain all the 3 valid characters or choices that we can make or build our strings with, A, B, and C. And this is also going to help us iterate through the valid choices in lexicographical order, right? A, then B, then C. A is lexicographically smaller than B, which is lexicographically smaller than C, right? Now let's actually get our 2 integer variables, or rather our 2 return variables, the count and the result. And the count, of course, that's simply going to be the number of valid strings that we see. That's simply going to be initialized to 0 because, of course, we're starting off with 0 valid strings. Then the result is going to be that kth string that we want to actually output. That's going to be initialized to an empty list, but effectively, once we find that number or k number of happy strings, we're going to return that result to be whatever it is. So now let's actually get into the recursive or helper backtracking function to actually recursively build all of our valid happy strings. And I'm literally just going to call it backtrack like I usually do for my backtracking or just recursive problems in general. And it's going to take in exactly 1 parameter. That parameter is going to be the current string that we're building in this iteration. Right? Now, this is basically going to, again, recursively build all the valid happy strings, where in one call or one iteration of this function, we're going to be working on 1 current string and building that until it has a length of n, and we're checking if it is valid. Right? So before we actually get to do anything or any operations with this backtracking helper method, notice how we initialize count and result outside of this function, outside of this nested function, right? So we want to actually make them non-local, or access the non-local variables of these, or access the non-local variables, count and result. So I'm going to use a non-local keyword, and I'm going to get the count and the result. Right? All this is really doing, basically, we have to actually modify the count and the result inside the function. So we have to actually declare them as non-local variables because we already defined them up here outside of the nested function, so we can actually work with those corresponding same variables. Now, what is the first base case or conditional that we want to check in this helper function? Well, that is, what if the current string equals n? So if the length of the current string that we're currently building in this iteration, what if it's equal to n, meaning we have n characters, we do satisfy this as a happy string, because note that we want to actually get all the list of all happy strings of length n. So if this is the case, we found 1 more happy string of length n, and we want to increment our count by 1, because again, the count is going to store the number of valid or happy strings of length n that we build or find, and we want to return the kth value of that list, right? That means the current string basically has reached n characters. We want to increment the count by 1. Now, in the same conditional here, what if the count now, what if that's equal to a? Meaning, what if we've actually found this next current string? What if we've now reached a k count? Meaning, what if we've actually reached k valid strings in what if we've actually built k valid strings so far in up to this conditional or up to this iteration? If that's the case, we want to immediately return our result, and that result would simply be the current string. So technically, I could just return the current string, and for some reason I'm only realizing this now, but I'm gonna actually use the result variable like how I talked about it. So I'm gonna get the result and store it to be the current string, and then immediately return. Right? Basically, very straightforward here. We're storing that result or that string in the result, and we're stopping any further recursion from this execution or from this function call. Right? Because of course, we don't want to keep going with recursion. If we found exactly k valid happy strings, we want to just get a result and just return. Right? We just want to stop the recursion. So now let's actually begin iterating over the list and actually building our characters, or actually building our strings, right? So basically for C in the characters, C is basically going to be our iterator, right? And we're going over A, B, and C in that lexicographically ascending order, right? Chars is again this A, B, and C list of length, of course, 3. Now, in every iteration that we actually loop through A, B, and C, what if the current string, so if the current string, if it's actually non-null, and the current string at the -1 value, or at the topmost value in Python, if it's equal to the current element, what does that tell us? Well, we know for a string to be happy, or for a string to even be valid, we know that the no two adjacent characters have to be equal. So if the current element, A, B, or C, if it's equal to the topmost element, or the most recent element that we've just added, we know that we can't add it because, of course, we would get adjacent characters that are adjacent. And so if this is the case, we immediately have to continue. That means the last character of the current string is the same as the current element that we're trying to add, C. We have to skip it to maintain that happy string conditional. So we simply have to continue on to the next iteration of this for loop, consider adding the next element. Now, if the result is non-null, meaning if we do actually have a result, it's already populated. That means we've already found the kth happy string. We can also simply just stop further recursion, and we can simply return. That means that we've already got our result to be some current string. We've already initialized it and declared it to be that current string result. And so if that's non-null, meaning we already have a result, a resulting string that is, we immediately have to stop further recursion. We just immediately return, right? And then effectively, this is the as such main recursion part, main call of this function. Now we actually have to call backtrack, right? If we don't call backtrack, well then we won't be able to do anything, right? This is the main recursion part of this solution. And so the way I'm going to do this is I'm just going to have a recursion or a recursive call in this for loop here for every iteration. And basically the way it's going to work is I'm going to call backtrack. And I'm going to pass in the current string to whatever that is right now, whatever number of characters that it has right now, plus C. That basically simulates adding the current character C if it passes all of these conditionals to the current string, right? We're basically appending C recursively to the current string and calling that backtracking function using that recursive or recursively call, right? And effectively, if this isn't the case, otherwise, if that result isn't true yet, but then we have to actually call recursively backtrack with the current string or with the current character C being added to the current string, right? Then we move on to the next iteration or to the next call of the backtracking function. So that is it for the entire backtracking method. Now we have to actually call it and then return our result. So I'm just going to call backtrack. And of course, for our initial current string, since we haven't built anything just yet, we're just starting or initiating this call of the backtracking function. I'm going to initiate it with an empty list or an empty string. We have to start the recursion and start building off our current string from an empty string. That's how we initialize or start the recursion with. And effectively, once we actually get the result, we simply return it. And we would have built that result in this backtracking function non-locally. This result would simply contain the kth happy string, and if I were to submit this, unless I made any syntax errors here, this should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So on a high-level rundown, the way our solution actually works, basically we're actually defining that backtracking method or that backtracking helper function that's actually going to help us explore or actually construct or generate all the valid happy strings recursively in that range, and we're also using that counter to actually keep track of how many valid happy strings that we've actually generated so far to check if we've generated kth happy strings or not. And we immediately have to stop recursion as we actually find the kth happy string, because that would also reduce and optimize both the time and memory or space complexity, because we wouldn't be generating any useless strings after that kth string. And of course, if there are fewer than k valid strings, we simply return that empty string here. That means we never actually initialize our result to be the kth string. We'd simply return the empty string as it was, or as the resulting string was initialized to be, right? So for the runtime complexity, this is actually going to be a big O of 3 to the power of n. I know it's a very slow runtime complexity, but the backtracking algorithm is a very slow and brute force algorithm, right? It isn't known to be very fast, and that's why and the reason why is because, of course, it is a brute force method. We actually have to recursively explore all the possible valid choices to make at every single iteration, and that makes it quite slow. And that's why we also have quite small input constraints as well to actually accommodate for that backtracking algorithm. Right, so basically the reason why it's big O of 3 to the power of n, well, because we really have 3 choices on average in each iteration, or in each choice, right? Those 3 choices would be this A, this B, and this C. Those are the 3 choices we have, and at each iteration we have 3 different choices, or each position or index in the string has those 3 choices A, B, and C. And since we're generating strings of length n, in the worst case there would be 3 to the power of n recursive calls. However, technically, since we stop early, once we actually find the kth string, the actual number of calls would actually be much lower than 3 to the power of n, at least on average. But formally, this is actually a big O of 3 to the power of n runtime complexity, right? And for the memory or space complexity, it is really just linear. It's really just big O of 1, because, of course, big O of n, that's a linear memory or space complexity. Why? Because in this case, for the context of this problem, the recursion depth would be at most n, and so the space that would be used by that call stack would be also big O of n. And unlike any other previous backtracking solutions, we don't actually have to store all of our valid happy strings like we saw for other Leetcode problems where we have to actually build up all the valid strings and return that list as a whole. We don't have to do that, and that would also reduce our memory usage significantly, right? So the overall memory or space complexity is also big O of n. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.